Okay, so in the previous video we have seen how to apply Lagrange's theorem and counting formula, and before that we have seen how to define cosets of a subgroup in a group. And in this video I am going to introduce to you a very important notion of group theory, namely quotient groups. Okay, this is a very important notion that is used all the time in group theory. So it's important for you to carefully understand the notion and be able to apply various theorems and properties of quotient groups that we will study. So I'm going to introduce to you what quotient groups are using some definitions and some properties. The basic idea is the following. You have a group G and H a subgroup of G. In the previous video I introduced for you the notation G mod H, right? G mod H was this set of all left cosets of H in G. So in other words, these are all elements of the form AH, where A is in G. To begin with, this is just a set, and we computed this set in some cases. For example, when G is the group of integers under addition and H was some subgroup of the form NZ, and I think we worked out the case of 4Z in our example. The set of left cosets was a finite set actually, and we listed them. Similarly, when G was the group of bijections of a 3-element set, namely symmetric group on 3 letters S3, and we looked at some subgroup H and we wrote down all the cosets of that subgroup, right? So this is the set of all left cosets. So our question is that will motivate the definition of quotient groups is, can we give a group structure to G mod H? This is the basic question that I want to address. Can we give a group structure to the set of left cosets of H in G? So in other words, what is a group structure? It is a, first and foremost, it's a binary operation. So given AH and BH in G mod H, can we perform something? Can we get, after performing some operation, third left coset out of AH and BH? Okay, so this is the question. So question is, can we give a group structure to G mod H? And in order to do that, first we want to define a binary operation in G mod H, so that when you apply that to two cosets AH and BH, we get a third coset. Okay, we want to do this in general. Now a specific example you may be able to do it, but the hope is that we should be able to do this in general. And not only, of course, this is not the end of it, right? We have to, after giving this binary operation, we have to make sure that there is a identity element, that this group operation admits inverses and it is associative. These must be checked. So let's see whether we can do something like this. So I'm going to recall for you the example we worked out. Okay, so let's take G to be the symmetric group on 3 letters and H to be the subgroup of E and 1, 2. And if you recall, we computed the cosets of this very carefully. So in particular, we computed what is 13H. 13H was, so I'm going to just write this, it is something that we already did. Okay, and let me work with another element 23H. 23H was 23 and 132. we already saw this. Okay, so in a previous video we have done this. So what do we do? Can we combine them? So what is 1213H? What should be 13H times 23H? Okay, so it looks like we have to learn how to multiply sets. We know how to multiply elements. So one attempt would be, so now very generally, let me introduce to you a notion. G is a group, A, B are subsets of G, not subgroups. Okay, so I am not taking not subgroups, not necessarily subgroups. They can also be subgroups, but I am not restricting only to the case of subgroups. Define. So because I am doing this because it seems like we have to multiply two subsets of a group here. In order to multiply 13H and 23H, we have to multiply two subsets. So let's define A dot B to be simply A times B, where A is in A and B is in B. Okay, this is just the product set. Very natural definition, right? In order to multiply two sets, we simply take elements of the first set, multiply them with elements of the second set, and you vary all the elements. Okay, so can we use this definition? Because cosets, remember, are just subsets. Left cosets are nothing but subsets, and I have told you how to multiply sets of a group, subsets of a group. So using this to calculate the two cosets we are considering here, 13H times 23H. I need to remind you again, this is not, I am not claiming that this is a group operation, this will work out. I am just saying this is an attempt, because we need to multiply, here we have to multiply sets, right? The goal is to multiply sets. So if you want to multiply sets, this seems like a natural definition of set multiplication. So let's just do 13H times 23H. And as I said, 13H and 23H are, we listed them earlier. It is simply the set 13, and let's see, 13H was 13, 1, 2, 3, product with 2, 3, 1, 3, 2. Right, these are the two left cosets. So let's multiply them. What is this? You take 1, 3 and multiply by, you take an element from the first set. In my definition, I take this to be A, take this to be B. This becomes 1, 3 times 2, 3. Okay, so 1, 3 times 2, 3, 1, 3 times 1, 3, 2, 1, 2, 3 times 2, 3, and 1, 2, 3 times 1, 3, 2. Okay, those are the four products we have. So I take the first element of A, now 1, 3, multiply by 2, 3, because that's an element of B. I take 1, 3 and multiply by 1, 3, 2. Similarly, I take 1, 2, 3, multiply by 2, 3, 1, 2, 3 times 1, 3, 2. So these are the four products. Let us just simplify these and see what we get. What is 1, 3 times 2, 3? So I will just quickly do one of these and then write the rest. So remember the product in the new notation for S3. How do we multiply? So you start with the right hand side element and go to the left. So 2 goes to 3 and 3 goes to 1. So this is 2, 1. What does 1 do? 1 is fixed under 2, 3 and 1 goes to 3. So this is 2, 1, 3. 3 goes to 2 and 2 goes to 2 in this side. So this is 2, 1, 3. Similarly, 1, 3 times 1, 3, 2 is 1 goes to 3, 3 goes to 1. So 1 is fixed. 2 goes to 1, 1 goes to 3. So 2 goes to 3 and 3 must go to 2, as you can check. 3 goes to 2 and 2 goes to 1. Similarly 1 2 3 times 1 2 3, 1 goes to 2 because 1 is fixed here, and 1 goes to 2, 2 goes to 3, then 3 goes to 1, so 2 goes to 1, 3 goes to 2, 2 goes to 3, that's fixed. Finally 1 goes to 2, sorry 1 goes to 3, 3 goes to 1, so 1 is fixed, 2 goes to 1, 1 goes to 2, so 2 is fixed, and 3 goes to 2, 2 goes to 3. So this is actually the identity element, right? So the last product is the identity element, and this of course can be rewritten as 1 3 2. So this is another subset. So I am going to just rearrange these elements: E, comma 1 2, comma 2 3, comma 1 3 2. Okay, so now let's stare at this. Earlier I have defined taken two subsets and defined their product. It is another subset. So here I have taken two subsets consisting of 2 elements each, and I multiplied them. I got a subset of 4 elements. Now in order for this operation to be a valid group operation on the set of left cosets, when I multiply left cosets, I must get another left coset. So is this a left coset? Is this a left coset? We computed the left cosets of this subgroup, right, in an earlier video, and either by looking at it, looking at the list of cosets that we computed, or using counting formula. Counting formula says the number of left cosets, elements in a left coset are equal to the elements of H. Remember, cardinality of H is equal to cardinality of AH for every A in G. So any left coset of H must have same number of elements as H, but AH has 2 elements in our example. So any left coset must have 2 elements, but this has 4 elements, so this cannot be a left coset, right? You can either check the explicit list that we calculated earlier, or use counting formula. Use the not the counting formula really, it's the theorem that cardinality of H is the same as cardinality of AH. This was used in Lagrange's theorem and counting formula. So this cannot be a left coset, so this is too bad. We cannot use this definition to give the definition of a multiplication of 2 left cosets. And however, I want to now illustrate that it's actually not such a bad definition of product of left cosets. We only need to ask for a slightly stronger condition on a subgroup. We need to impose conditions on subgroup. So the conclusion is this product of left cosets is not a valid binary operation. It's not a valid binary operation because product of 2 left cosets is not a left coset in general. So in general, product of 2 left cosets is not a left coset, so it is not a valid binary operation. However, we will show in the next few minutes this is a valid binary operation if H is not just a subgroup, but H is a normal subgroup. So if H is a normal subgroup, it turns out that it's this product that we define here, AB equals capital A times capital B is small a times small b. As you vary elements of capital A and capital B, that becomes a valid binary operation provided that H is a normal subgroup. Okay, so this is what I want to show, but before that let me prove a proposition to achieve my goal, to show the following. So suppose that H is normal in G. So typically we denote normal subgroups by N. So in this case I will stick to H, but subsequently generally when we talk about normal subgroups we use the letter N. So what I want to first show is if A belongs to G, then AH equals HA. Okay. So if H is normal in G, AH equals HA. In other words, the left coset AH is equal to the right coset AHA. Let's prove this. Okay, this is not difficult. So I'm saying, in fact, I'm saying that if H is normal, AH is equal to HA. I'm also saying the converse, but I'll write that later. So I'm saying AH equals HA. What does that mean? I want to prove that the set AH is equal to the set HA. What does this mean? What is AH? We want to show that AH as H is in H is equal to HA as H is in H. So an important warning for you, we are not saying AH equals HA. In other words, if I replace capital H by small h here, I can't say this. See, this is too much to expect. This is saying that if you recall the definition of if this happens for every A, this means that H is in the center of a group, if you recall the definition of center of a group. But H can be normal and not be in the center of a group. So I'm not saying this. Why am I not saying this? This is a weaker statement because I'm saying that A small h is equal to H small h times some other small h times A. So we only need AH to be in HA. Okay, it can be it need not be this particular small h times A, it can be some other h prime times A. So it's very important to keep in mind that to say that these two cosets are same is not same as saying the element A times small h is equal to the element small h times A. So now let's prove these two sets are equal. How do you in general prove two sets are equal? You want to show that the first is a subset of the second and the second is a subset of the first. So to prove this equality, choose or let AH be in AH. Okay. So if AH is in A capital H, let's rewrite this like this. Right? AH is equal to AH A inverse A. We can write it like this, right? Because by associativity, A inverse and A can be first multiplied and that is identity and you have AH. So, but then since H is normal in G, this is where we are using the normal hypothesis. Given A in G and H in H, A inverse belongs to H, definition of normal subgroup. So this is in H, I am calling it H prime is in H, this is by definition in H here. So if you take an arbitrary element of the left coset, it is in the right coset. So AH is a subset of HA and the opposite is identical. Okay, so you can do this by symmetry, but let me just illustrate the point again. If it's not clear to you, hopefully it will be clearer after this. Let's take an arbitrary element of the right coset. Then what we write as before, let's write it as A times A inverse times HA, right? That is same as this because of associativity. But if AH A inverse is in H, this is also in H, right? So this is H, so call this equal to H double prime. AH double prime, and this is by definition of a left coset is in AH. So every element here, arbitrary HA is in AH. So HA is in AH, hence AH equals HA. Okay, so as an exercise, so this completes the proof of the proposition. Proposition only asked you to show if H is normal, then AH equals HA for every A. I want to leave this as an exercise for you, and this is a easy exercise that you must do. If H is a subgroup of G and AH equals HA for all elements of the group, then H must be normal in G. So if this property holds for every element, then it is actually normal. That we don't need, so I will leave it as an exercise for you, but you should do this. And actually another exercise, if G is S3 and H is the subgroup we considered earlier, E and 1, 2 is 2, 3 times H equal to H times 2, 3. Okay, so this is the question. The left coset of 2, 3 is it equal to right coset of 2, 3. So I'll do this, give these exercises to you. You should do this. This 2, 3 H we already computed. Just compute H 2, 3. Okay, this if you compute, you will see that then you can ask if it's equal or not. Okay, so now let's come back to normal subgroup. So in a normal subgroup, we have AH equals HA. Now I'm going to prove the main result that we want. Proposition. Suppose that H is a normal subgroup of G. Okay, then AH, then let A be in G. So I'm taking two arbitrary elements of G. AH times BH is by definition, this is the product of two sets that I have defined earlier. So this is the product of product of these two cosets that we defined earlier. Namely, you take something in AH times something in BH and multiply. You do this for every element of AH and every element of BH. And we saw in the example of S3 and H equal to E and 1, 2 that the product is not a coset, but in this case it becomes a coset. It is the coset actually AB times H. Okay, so if AH and BH are two cosets, their product is also a coset. Let's prove this. This is not difficult now. Okay, so we already know by the previous proposition what do we know? So we know that HB equals BH, right? So let me write that here. So HB equals BH. So now let's compute this. AH times BH. See, remember, just to illustrate, so I will just start in the new page. AH equals AH times BH. Because of associativity, I can write this as A times HB times H. Okay, so why is this? So it might be useful, it is true, but it might be useful to actually write down this. What is AH times BH? You take something in the left coset AH, it is of this form, and you take something here, so BH prime. So you take this as you vary H and H prime in right? This is exactly the product of two sets in a group that we defined here. If you have two group subsets of a group, the product is defined to be AB, where A is in A, B is in B. This is the definition of product of subsets that we will always use. So in this case, I am applying this definition to AH and BH. AH is the set A small h, BH is the set B small h prime. I just want to use a different letter because it is, you have to vary all elements of capital H. So AH times BH. But this, if you use associativity of group product, right, then this becomes, so I can vary H and H prime, two distinct elements, two may not be distinct, two elements of H. Then I have AHB H prime, but I put the bracket around HB. But this is precisely this, because HB, capital HB is all elements small hb and capital H is small h prime. So these two are equal, okay, so this is okay. I will erase these two are equal. But now by the same associativity, I can write this as, first of all, use the property that I said earlier, HB equals BH. So I can interchange. Remember, I cannot interchange B and small h, but HB equals some BH double prime. So that BH double prime will come here. So in other words, I am saying that A, B, H double prime, H prime, H double prime, H prime in H, right? So this is the, this part can be interchanged, switched like this. So this is what I have. Now again using the same, this is this. Again using the same associativity, I can write this as AB times HH. But what is HH? If you think about it, it is nothing but H. So we claim HH equals H. Why? What is HH? It is a product H times H prime. H and H prime are in, right? So, but if H and H prime are both in H, H prime is in H. So this is actually contained in H. HH is contained in H. On the other hand, if small h is in capital H, you can write this as H times E, and this is in HH, right? Because E is in H, identity element is in H is in H, so HE is in HH. So this means H is contained in HH. So HH is contained in H is contained in HH. So this implies H equals HH. When you multiply a group with itself, you don't get anything bigger. You get exactly the group. This is not true in general for a subset only, which is not a subgroup. So H is equal to HH because H is a group. We have used both properties, right? Here, because if H and H prime are in H, the product needs to be in H here, and E is in H. We need, so E, in order for H is equal to HE, right? But for that we need E to be in H. So because, so here we use the other important property of a subgroup. It must contain the identity element. So see, now we are done, right? Because AHBH is AHBH, which is ABHH, which is ABHH, which is ABH. So AHBH is equal to ABH, which is what we claimed. So this is the theorem. So this proposition allows us to define this proposition define a group structure on G mod H when H is normal. Okay, it turns out that there is no natural way to define group structure on G mod H when H is not normal. This can only be done when H is normal. Okay, so what is the group structure? So now, from now on, assume that G is a group and H is a normal subgroup. Okay, so I'm going to assume that always I'm dealing with a normal subgroup of a group G. Then we will give a group structure to G mod H. Okay, so first of all, recall what is G mod H. This is the set of left cosets as you vary A in G. So what is the binary operation? Remember, the definition of a group is you start with a set and define a binary operation on the set and verify that there is an identity, every element has an inverse, and the binary operation is associative. So what is the binary operation? It is the one we discussed earlier. So define AH star BH. I am using star just to emphasize that it's a new binary operation we are defining, is the product ABH. Okay, so this is the definition of binary operation. Now, is there an identity element? It's simply H. See, H itself is a left coset, right? That is identity element. Why is that? So you take AH star H and this is AH because A star E is A. Similarly, H star AH is AH. Okay, so this is an identity element. What is the inverse of AH inverse? Clearly must be A inverse H, because AH times A inverse H is by definition A inverse times H, which is EH, which is H. Similarly, A inverse times H times AH is A inverse AH, which is EH, which is H. And associativity, finally, if you take AH times BH, then take CH, this is ABH times CH, which is by definition ABCH. Remember, ABC you can multiply in any order because this is happening in capital G. So in group G, the product is associative. See, as you can see, I've started not writing star. So if there is no star, I am just multiplying using this definition. So ABCH. On the other hand, what is AH times BH times CH? This is AH times BCH, which is, so really what I have should write here is AB times C. Here I have ABC times H. But these are equal because AB times C is A times BC. So associativity is also clear. The point is that you needed a valid binary operation. That was the key step. If you have a valid binary operation, it turns out that the others are more or less clear. Identity element is EH, inverses are given by inverses of these elements. Associativity is essentially the associativity in the group itself. There is, and that will give associativity of G mod H. Okay, you might wonder, can I just define this without H normal? As I said, if you just declare it like this, many of the properties you cannot check because AH star H would be, the product is no longer going to be AH if H is not normal. Okay, so if you just declare it without the normality hypothesis, this will not give you a group. Okay, so this is the quotient group that we wanted to discuss in this video. G mod H with this group structure is called the quotient group. Okay, so the quotient group is defined, this is defined only when H is a normal subgroup. Okay, so and quotient groups come with an important homomorphism. There is a from G to G mod H. Okay, what is that? You take A and you simply map it to AH. This is the set map, A going to AH, because G mod H, remember, is the set of left cosets. A is an element, AH is a left coset. Why is this a group homomorphism? Why is phi a group homomorphism? Why is phi a group homomorphism? Let's check this. We want to check phi of AB equals phi of AB, right? Sorry, phi of AB equals phi of A times phi of B. Is this true? Let's write down what is phi of AB. Phi of AB is by definition ABH, right? And phi of A is AH, phi of B is BH, and these two are equal by definition of the product. AH times BH is equal to ABH. So this is a group homomorphism. Okay, so quotient groups must always be thought of with this structure of this particular group homomorphism. So it is a group and it admits a natural homomorphism always, G to G mod H. What are the properties of G mod phi? We can say the following. Kernel of phi, remember the kernel of phi is all A in G such that AH is equal to the identity element of right, this is the by definition the kernel. What is the identity element of G mod H? So this is all A in G such that AH equals EH, which is same as H, right? So I don't need to write EH, I'll just write AH. The identity element of G mod H, remember, is H. So it is all elements that map to H. But what is this? When is AH equal to H? This happens precisely when A is in H. This is something we have discussed earlier. So this is H. So kernel phi is H. What is image phi? What is image phi? It is AH. Image phi is by definition phi A in G. That means this is AH with A in G. This is precisely GH, right? G mod H. You have all the left cosets here, so it's G mod H. So in other words, phi is on 2. So kernel phi is H and phi is on 2. So I'm going to summarize all this that we learned about quotient groups and write the following. If G is a group, and H is a normal subgroup of G, then the set G mod H of left cosets of H in G is a group under the operation AH times BH equals ABH. Okay, this group G mod H is called the quotient group. it's a quotient group of H, quotient group associated to G and H. It comes with a natural group homomorphism phi from G to G mod H, which such that, so we have checked that phi is a group homomorphism, right? Such that phi is onto and kernel phi is H. Okay, so this entire thing you need to remember. So read this carefully. We can construct quotient groups whenever you have a group and a normal subgroup, and the underlying set for the quotient group is simply the left cosets of H and G. So I want you to think of quotient groups as something very easy, okay? So it's not difficult at all, because you know what is the set of G mod H. It is simply the set of left cosets. A group is a set with a binary operation, right? So you know the set here, which is G mod H. It is a set of left cosets. What is the operation? We need to give it an operation to make it a group. It is simply you take AH and take BH. When you multiply them, you get ABH. So that is the group operation. And it's easy to check that this group operation is closed, has identity, has inverses, and is associative. Not only that, quotient groups must always be thought of along with this crucial natural group homomorphism from G to G mod H, which has two important properties, namely that it is onto and its kernel is H. Okay, so these are the properties of quotient groups that we want to emphasize.